Hello everyone, my name is Fibin Abram and in today's video we'll be talking about electric current. So let's get started. So as the name suggests, electric means we're talking about electrons. Current means something which is moving, right? So when I say electric current, that means when your electrons are moving, right? So when your electrons are moving, that is something which we call as our electric current, right? Now the important thing that comes is how you can measure that electric current, right? Okay, so for that I have a copper material. Now copper is the most common material which is used as connecting wires in our homes, right? Now why it is used? Because it is a good conductor of electricity and it has a high melting point, right? And it has a lot of free electrons inside which can actually move, and because of that we can get the charge, right? So you guys can see I have this copper material, and you guys can lots and lots of free electrons are there inside that copper material, right? Okay, now what I'm going to do here is I'm going to connect it with an external battery source. The moment I connect it with an external battery source, what is going to happen? There will be a potential difference across the material, right? Obviously this part will be positively charged and this part will be negatively charged, and because of that what is going to happen? These electrons will start moving and they will be attracted towards the positive plate, right? And what is going to happen? So your electrons will start moving, right? So because of the movement of electron, there will be a current. Now remember, if your electrons are moving like this, right, if the electrons are moving like that, then the current will be in the direction opposite to that of your electron movement, right? The current will be opposite to that of the movement of your electrons, right? I hope you guys can understand that, right? Okay, now how I'm going to measure the current, right? Now for that we're going to use a simple trick. What I'm going to do here is I'm going to make a small cross section there, right? I hope you guys can see the cross section. So I have made a small cross section, and let's say I'm actually here, right? I'm actually standing there and I have a stopwatch, right? I have a stopwatch with me. So I will calculate how much electrons or how many electrons are passing this cross-sectional area, in some amount of time, right? Obviously with the help of stopwatch I can actually see how much electrons are passing through this cross-section area in some time, right? And that is how we actually measure the current, right? That is how much charge has been passed per unit time, and that is what we call as our current, right? I hope that is understandable, right? Great. Now let's talk about the SI unit of current. Now SI unit of current, obviously current is written as charge per unit time, that is Q upon T. So the charge has a SI unit of coulomb and time has a SI unit of second, right? So coulomb per second is actually represented by ampere. Now ampere was the name of scientist who actually discovered this phenomena, so it is named after ampere, right? Now 1 ampere is that quantity of current when 1 coulomb charge passes through this cross-sectional area in 1 second. So 1 coulomb charge has been passed through this cross-sectional area in 1 second. Now you have to understand 1 ampere current is a very large unit of current. That's what I was saying. So 1 ampere current is a very large unit because 1 coulomb charge has been passed through that cross-sectional area in 1 second, right? That means 6.25 into 10 to the power 18 electrons has been passed through this cross-section area in 1 second. That is huge number of electrons, right? So obviously 1 ampere current is always a huge or a large quantity of current, right? Okay, next point, the current is always in the direction opposite to the flow of electrons. Obviously the current will be always, for example, if electrons are flowing in this direction, the current will be in the opposite to that, the flow of your electrons. I hope that is understandable. Let's discuss some general cases. So the domestic appliances that we use, so those domestic appliances will be having a current of approximately 1 ampere to 2 ampere, right? So that much is the maximum current that our domestic appliances, for example our laptops or our TVs or our CPUs, fridge, refrigerators, so all these our domestic appliances use approximately 1 ampere current, right? 1 to 2 ampere current is the maximum limit for them to use, right? Next is, obviously we have heard of lightnings, right? Lightnings happen just, obviously at the time of rain or just before the time of rain. So lightning carries a current of approximately 10 to the power 4 ampere current. This much current is being carried by the lightning. So that's why it is always advisable to never to get struck by a lightning, because this much ampere current will pass through your body, and definitely you will fry yourself, right? Okay, great. Next, we have electric current inside our body also, right? So our brain sends electrical signals. Now those electrical signals are of the order of 10 to the power minus 6 ampere, right? So current in our nerves, so nerves actually transfer your signals from the brain in the form of electrical signals, and that has a magnitude of 10 to the power minus 6 ampere, right? And that is equals to 1 microampere. I hope that is understandable. Okay, now important thing, that current is actually a scalar quantity. Although current has a magnitude, and also we just saw that current also has a direction, but still current is a scalar quantity. Why it is that? Because the current does not follow vector law of addition. Now when I say vector law of addition, you must have seen whenever there is a junction, the current divides at the junction I1 and I2, and it does not depend upon at which angle it is actually dividing, right? So it does not follow any kind of vector law. So in order for any quantity to be vector, it should actually follow the vector law of addition. Otherwise we cannot say that it's a vector quantity, right? So very similarly, your current does not follow the vector addition. That's why we say your current is not a vector quantity, it is a scalar quantity, right? Okay. In fact, actually current is not scalar also, it's actually a tensor quantity. Now we will discuss about that, we don't have to discuss about that here. But anyway, just for your understanding, you should understand current is not vector, but we can say it's scalar, but actually it is a tensor quantity, right? Okay, great. Now let's move to the next part. Your current can be measured in two different quantities. Basically you can measure the average current and you can measure the instantaneous current. Now when I say average, so obviously now how you measure an average of any quantity, right? So obviously you add up the quantities divided by number of quantities, and that is how you find out the average, right? Very similarly, average current is the total number of charge passing through a conductor in a time interval. Obviously for a particular cross-sectional area, so in let's say in 0 to 2 seconds, how much charge has been passed through that cross-sectional area, that is the measure of average current. That is change in your charge, right? That is how much charge has been passed through your cross-sectional area in change in them. That is how much, for example, let's say from 0 to 2 seconds, let's say this much amount of charge has been passed. So when you calculate this, you will get the average current, right? Okay, next one is your instantaneous current. Instantaneous current means you want to find out the current at any particular instant. For example, I want a current which is like passing through my cross-sectional area at t is equals to 3 seconds. So at 3 seconds, I have to find out the current. So here is where instantaneous current, the concept of instantaneous current comes into act, right? So that is the amount of charge passing through a conductor at a moment of time, right? So at a instant of time, how much current that is passing through your cross-section area, that is your instantaneous current, right? So instantaneous current is I at any time t is simply given as dq upon dt, right? Where dq is a small current, obviously at a particular instant a small current will pass through, and obviously in a small time, so that's why we just write it dq by dt. I hope that is understandable. Okay, so for all those who still are confused about your average current and your instantaneous current, let's do a problem so that we can understand it much better, right? So problem says if your q, so this is the charge, that is 3t square plus 4t plus 6 charge flowing through a conductor, so this much charge is flowing through a conductor, then you are supposed to find out the current at t is equals to 2 seconds. So first thing that you have to understand here, the first thing that you have to find out here is the current that is flowing at t is equals to 2 seconds. Next, you're supposed to find out the average current from 0 to 2 seconds. So current at t is equal to 2 seconds means I'm supposed to find out the instantaneous current at t is equals to 2 seconds, and I'm given the value of charge, that is 3t square plus 4t plus 6. Okay, so let's try to do this. So current at 2 seconds, that is your instantaneous current, will be simply given as, we know this is the formula, dq by dt, right? Now I at 2 seconds, so I at 2 seconds simply can be given as d by dt multiplied by the q is actually given in our question, that is 3t square plus 4t plus 6. So I can, instead of q, I'll just write it here and I will differentiate it with the respect to time, right? So 3t squared, when you differentiate it, 2 will come out, you will get 6t. 4t differentiated, you will simply get 4, and 6 is a constant, so constant will have a differentiation of 0, so we will get a 0 over here. So I at 2 seconds, so wherever there is t, you just put the value of, you know, t to be 2 seconds. So when I write it, this will be 6 multiplied by 2 plus 4, 16 ampere will be the instantaneous current at t is equals to 2 seconds. I hope that is understandable. Great. Now let's move on to the average current. Now average current you have to find out from 0 to 2 seconds. So from 0 to 2 seconds, how much charge has been passing through your cross-sectional area. So that is something which I have to find out, right? So I average has a value of del q, that is change in charge upon change in time. That is how much charge has been passed from q is equals to 2 minus q is equals to 0. So from, obviously you are supposed to find out from 0 to 2 seconds, right? So I will find out at what is the charge, how much charge has been passed at q is equals to 2 and how much charge it was at q equals to 0, right? Divided by t2 minus t at 0, right? So q at 2, so for example, obviously you know the value of q here. So here wherever there is t, just put the value 2, so that is 3 into 2 square plus 4 into 2 plus 6. So 3 into 2 square, that will be 12 plus 4 to the 8 plus 6. So this is 14 plus 12. 14 plus 12 will be simply equals to 26. We will get 26, right? So here you guys can see here you have 12 plus 8 plus 6, that is 26, minus q at 0. So q at 0, wherever there is t, just put the value. This is 3 into 0 plus 4 into 0 plus 6. So you are simply left with the value 6. I hope that is understandable. So put it over there. So this is 12. Okay, great. Minus 6 divided by t at 2 is basically 2 minus 0. That is 2 minus 0. So when you calculate it, you will get 20 upon 2 and 10 ampere. So average current from 0 to 2 seconds is coming out to be 10 amperes. So both the currents are different. You guys can see instantaneous current at t is equals to 2 is 16 ampere, and average current from 0 to 2 seconds is actually 10 amperes. So I hope this example has made things clear for you, right? Okay, so let's try to solve one more question, and the question is, in a hydrogen atom, the electron makes about 0.6 into 10 to the power 16 revolution per second around the nucleus. Okay, so in a hydrogen atom, so there is a nucleus. You guys can see there is a nucleus and there is this electron, and this electron revolves around this nucleus. We are supposed to determine the average current at any point on the orbit of electron. You're supposed to find out the average current at any point on the orbit of electron, right? So obviously you have this, you guys can see there is this nucleus, the electrons are revolving around. So assume a small cross-sectional area. So from that cross-sectional area, the electron is actually going. So I'll simply assume that this electron take, let's say, some t time, from 0 to t time, it takes some 0 to t time to obviously complete one particular revolution, right? So let's say so I can write it, I average is actually equals to change in q. Obviously, what is the charge that is going? That is the charge of an electron which is actually moving, divided by, let's say, some t time it takes for the revolution. I hope you guys can understand. And I can, in the next step, I can write it as frequency. Why? Because 1 upon t is represented as the frequency. Now in the question, we are actually given the frequency. The electron makes about 0.6 into 10 to the power 16 revolution per second. So this is actually the frequency information that is given in the question. So basically I can write it E multiplied by the frequency, right? So in the next step, I know the charge of an electron is actually minus 1.6 into 10 to the minus 19, and the frequency is this much. You multiply it, you will get 0.96. I just omitted the negative sign because I want to find out the current. I'm not interested in the direction of the current. So 0.96 into 10 to the power minus 3 ampere, that is equal to 0.96 milliampere, right? So whenever there is a circular motion, we can use this formula to find out the current, that is E multiplied by the frequency, right? So I hope you understood the video about electric current. If you have any doubt, you can comment it down in the comment section, right? So that's all for today. Thank you and have a nice day.